Now we're recording. Okay, so example 6. Find the point on the curve y equals cosine x closest to the point 0, 0. So in section 3.6, title is optimization. So we are finding maxes and mins. So we are maximizing things or we are minimizing things. So we end up taking the derivative every single time in these problems. And in order to find a max or a min, you set the derivative equal to 0 and solve. So in this problem, are we finding a maximum or are we finding a minimum?
Minimum.
Right, because the word in the question is closest. So we are minimizing. Okay, and it doesn't matter whether you're maximizing or minimizing, you're still going to take the derivative either way, and you're still going to set it equal to 0. So it's not going to change your process. The question is, what does this look like? That's what my question is. So let's see here. So from trig, we should all remember what a cosine curve looks like. Kind of starts up here, right? And it like goes down, does like this thing, keeps on going forever. Kind of goes like that, keeps on going forever. I tried to make that look symmetrical, but didn't quite happen, did it? So these two sides should be symmetrical, okay? And then, so this we know, this maximum up here, like this point, is 0, 1. And I know this spot right here is, what is this? What's the x-intercept for the cosine curve?
Pi over 2.
Very good. Yep, pi over 2.
Pi over 2.
Yep. Okay. So pi over 2 is like 3.14 divided by 2. So 1.57-ish. So, all right, kind of. So we're trying to find the point on the cosine curve that's closest to the origin. Okay, so we're like right here, 0, 0. So the question is like, is it, and whatever happens on the right-hand side of the y-axis is also the exact same thing happening on the left-hand side, right? So like, it doesn't matter whether we go to the left or we go to the right. It would be easier to look at the right-hand side because these values are positive, so we don't have to worry about negative signs and all that good stuff. So the question is this point the closest? Is this point the closest? Or is it something in between that is the closest point to the origin? We know it's not going to be anything out here, right? Because that's beyond, that's not close. That's like starting to get far away, right? So it's none of this stuff. It's something in between here, or it's this one, or it's this one, right? Okay. So I need to take the derivative of something. So what are we minimizing?
Distance.
Distance, very good. So distance from yesterday is big square root, like this. And I know one of the endpoints has to be the origin. So you can put that in for x1, y1. You can put it in for x2, y2. Just for the sake of keeping it easy, I'm going to do x2, y2. So that way I just have it in the back. So this will be d equals the square root of x1 minus 0 squared, y1 minus 0 squared, like that. Okay. And you can put the little sub 1 there if you want to, not too big of a deal there with that. And so we're in that situation where we have two unknowns. You have two different variables. We want to get it down to one variable so that way we can take the derivative without having to do it implicitly. So what do I do now?
Replace the y with cosine x.
Yeah, very good. So here's your other equation that is your helper. They kind of just snuck it in there in the directions. So yeah, so d equals x squared plus cosine squared x, like that. All right, now we're gonna take the derivative of that. So dx and what will be the derivative of this?
It would be 1/2 times like x squared plus cosine squared x, but the square root of that on the bottom. Times 2x plus 2 cosine x times sine x, or negative sine x.
Yep, good. So you have chain rule, all kinds of good stuff in there. All right, so looks like I'm running out of space. So I'm probably gonna go on to notebook paper here soon. So what we're doing here is we're taking that derivative and you are setting this equal to 0, all right? And I marked that it's okay to use a calculator on this one because it's probably not gonna be, like with the trig here, I don't think it's gonna come out to be something on the unit circle that you have like memorized. So we might have to use our calculator. So if I continue, going here, actually, I'm gonna put that under my, yeah. Still crooked. All right, that's a little better. Okay, so remember, we got a fraction, we're setting it equal to 0. So that means really the only thing we care about is when the numerator is equal to 0, okay? So we're gonna have 0 equal to, let's see, how can we do this? 2x minus 2 cosine x sine x, like that. Now, some of you might recognize this. I'll bet you a lot of you don't recognize it because it often gets missed in your trig and pre-calculus classes. But this right here is actually one of your double angle formulas. So this is 2x minus, oh, no, nothing in front of there, sine 2x, okay? The double angle formula for sine is 2 sine x cosine x, or 2 cosine x sine x. same thing. So if that helps, it doesn't really help us that much in this problem. So that's why it's not that big of a deal if you don't remember it. But I just wanted to point that out. Corpy points it out in his work, so I figured we would do the same thing. But we're gonna need a calculator anyway. So I'm gonna open up Desmos, and let's see here if I can drag it over to the screen. You can use your graphing calculator if you want to. Basically what we need to do is figure out when that equals 0. All right, so what was it again? 2x minus 2x minus 2. I'm even going to put it in the old way just because it doesn't matter. Sine x, like that. Let's see if that's going to be an issue. What if I put y equals? Is that better? No, still doesn't like it. Maybe I need to put a times sign in there.
You have to put parentheses around the x in cosine and sine, probably.
Oh, does it think it's like all of that angle? Holy cow, look at that graph. All right, anyway, that's not the graph we want. Oh, but this one is, right? Thanks. Picky. These little calculators are picky. All right, what a cool looking graph. How about that? All right, so we're looking for the x-intercept. Well, the only one we got is 0. So that would mean that I kind of lost the whole graph, didn't I? That would mean if our x-intercept is when x equals 0, then our point would have an x-coordinate of 0. Okay, so that's where, let me organize myself a little bit better here. There we go. All right, so if your critical value, which is what we just found by setting the derivative equal to 0, and we used the graphing calculator for this, we only got one x-intercept, which is at 0. That means that our only critical value has to be x equals 0, but to find the y value, because I'm asked to find the point closest to 0, 0, so I need the y coordinate also. What would I do to figure out what y has to be?
Plug 0 back in the y equals cosine. X.
Yeah, very good. So you would have to do y equals cosine of 0. And what is the cosine of 0?
One.
1. Yeah. So it actually ends up being the point 0, 1, which is this spot right here. So you would think, well, actually, I don't know, maybe you wouldn't think, but a lot of times, you know, people don't think, oh, it probably is not the endpoints. Like it's probably not this and it's probably not this. But actually, this one turns out to be where it crosses the y-axis. All of these points on the inside between these two are bigger than this one right here, because cosine kind of, you know, when you have that curve, that means you've got to go out a little bit farther. So the closest point to the origin is actually that max point there at 0, 1. Okay. All right. So just as a reminder, this graph right here represents the derivative. And so you're looking for an x-intercept of the derivative, okay? And then to talk about this even further, kind of like to go back with what your test was on and stuff that we just took, see how, since this is a graph of the derivative, the y values to the left of 0 are below the x-axis. That means that your slope is going to be negative. And then your y values to the right of the of the y-axis are positive. So that means your slopes are then positive. So if I draw it, all right, so we do the little number line thing. So to the left of 0, you have negative y values. So we put a negative. To the right of the y-axis, you have positive y values. So that means your graph is decreasing and then it's increasing. So this has to be a minimum. Okay? Okay. All right, so let's go on to the next one. I just want to go on to the back. All right, example 7. Find the dimensions of the largest rectangle that can be inscribed under the curve y equals 16 minus x squared in the first quadrant. All right, so read it again. We're looking for dimensions of the largest rectangle. We got a curve that we need to graph, and we're only graphing it in the first quadrant. Okay, so draw a graph. What does the graph 16 minus x squared look like in general?
It's an upside down parabola, just up 16 units.
Right, good. So you got a vertex up here at 16, and it's doing like this, right? And it's going to do that on the other side too, but we don't care about the other side because we're only supposed to be focused on the first quadrant. Okay. Okay. We're drawing, what are we making here? We're making a rectangle with that. So the rectangle has to be under the curve. So that means like the corner point has to touch the curve, but it can't go like outside the curve. Okay, inscribed means it's inside the curve. So I don't know exactly how this rectangle is going to work. If I use my pencil, I mean, I don't know if it'll be like a tall and skinny rectangle, or if you're going to have like a short and kind of wide rectangle. I don't know. There's lots of different rectangles that we could draw. We just have to figure out what the biggest one will be that will fit in that space. So
Wait, if there aren't any changes to like multiplying the x or whatever in the equation, wouldn't those two rectangles be the same?
there aren't any changes to the x. If the x value is the same, yeah, the rectangles would be the same. The only thing is that we don't know what the x value is. Like we don't know if you have to go out 2 or you have to go out 1.5 or you have to go over 3.5. So the height is dependent on the width, but I don't know how far I have to go out. Did that answer your question or no?
Yeah.
Okay. All right. So we are looking for the largest rectangle. So we are looking for a maximum. And so if it's the largest rectangle, how do you determine how big, like what equation are we going to use to determine the size of the rectangle?
Would it be area or perimeter?
It's
One of those two?
area. It's area. Yes, the first one is correct. Area is like how much space, okay? Two-dimensional space something takes up, all right? So area is length times width, right? Or base times height, however you want to do this. I guess we did length times width in the other problems, so we'll stay with that. So I guess we'll call this length and we'll call this width. Now, if this were, you know, a concrete like example, like fencing in some land or, you know, just working with like square footage in a room or something like that, the L and the W would work just fine. But we don't have that situation in this example. We have the equation of a parabola. So we really can't use L or W here. We need to get it in terms of the coordinate plane. Okay. So, and we don't know either of these. Like, I don't know how far out I need to go in order to make the biggest rectangle under this curve. But I do know that if I travel along this axis, however far I go out, that's going to be X units because I'm on the X axis. So it'll have to be X. So I'm going to replace length with X. What can I replace the width with?
Y.
Right, Y. Now I still have two unknowns. I would really, because I'm going to have to maximize this, right? We're trying to find the maximum, the biggest rectangle. So I got to take the derivative of this, but right now I have two variables. I got to get it down to one variable. So how can I get this down to one variable?
Use the y equals 16 minus x squared.
Yeah, so this is going to help you. Put it in right there. So A equals X times 16 minus X squared, like that. All right, now the rest is piece of cake. So 16x minus x cubed. Now we're going to maximize it, so we take the derivative, dA dx. What's the derivative of that?
(16 minus 3x squared).
Yeah, good. Set that equal to 0. And solve for x. Okay, so take the square root of both sides. Technically, your answer would be plus or minus, but since we're working with the first quadrant only, we go with the positive answer. And your x value is 4 over the square root of 3. And you can leave it like that, okay? We need to know the other dimension, though. So if x is 4 over root 3, then y is going to be 16 minus 4 over root 3 squared. And then what is 16 minus 16 thirds come out to be?
Would it be 32 thirds?
Yep. So your height or your width, however you want to say it, is 32/3 units. And this is on the quadrant plane. So like you don't have to, you can just put units. And then 4/√3 would be your length, and that would be units. Okay. And that would create the rectangle that would take up the most two-dimensional space if it had to be inscribed under that parabola. Okay. So down here is some nice little like steps for those of you that like steps. If you want to take a screenshot of that, if you don't have it already, feel free. It's kind of wordy, but definitely gives you like every little thing, every little step. Also, a reminder at the bottom there that you can use the first derivative test or the second derivative test that we learned in 3.1 to 3.5 to help justify your answers, to show like this is definitely a maximum or a minimum. The big thing though is to make sure that your answer, this is number 6 right here, is like within a reasonable domain. Because a lot of times, well, almost all these problems, except for like this one that we just did, you're actually like building something or you're making something, like you're putting something together that would exist in the real world. And so you don't want negative dimensions and like stuff like that. So that's where we have to make sure that we throw out answers that like wouldn't make sense. All right. Everybody got that? Hopefully. I'm going to move on to example number 8. All right. Okay. All right, cool. Okay, example 8. An open top box is to be constructed from a square piece of cardboard 3 feet wide by cutting out a square from each corner and bending up the sides. What is the largest volume that the box can have? So think about this. We are looking for the largest volume. So we are looking to maximize volume. So we need to think of the formula for volume for a box, because that's the thing we're going to end up having to take the derivative of. So what is the formula for the volume of a box?
Length times width times height.
Good. There you go. Length times width times height. Now it's got 3 unknowns. So we're definitely going to need some help with that before we actually take the derivative. Okay. So that's where our diagram comes in handy. And I think I'm going to have to use pencil for this because I like don't trust myself. I always want to like modify something when I do these. All right. So this is what we have here. You have a sheet of paper. I'm sorry, not a sheet of paper. A square piece of cardboard. Square piece of cardboard. So that means that all these sides are the same. It's a square piece. And it's 3 feet wide. So that means like this whole thing is 3 and this is also 3. Okay. Now, what are we going to do? Well, we need to cut out some squares out of the corners so that we can fold up the sides of the cardboard and make a box. It won't have a top on it. It's an open top. So that means there won't be a top on this box. All right. So I got to cut out something here. I got to cut out something here. Here. That could have been a little bit better. Something here. Okay. We have to cut those squares off so that way I'll have the sides to fold up and like that, and we'll be able to create a three-dimensional box out of this. Now, all these little squares, in order for this box to fold up and have like a nice, like smooth, like everything's the same height all the way around, these squares have to be the same. Like they all have to be the same size. They all gotta, otherwise like our box is gonna be like all like wonky. We don't want that. Okay. Now, do I know how big of squares I should cut out of the corners? I have no idea. I'm trying to figure that out. And my goal here is to have a box that's going to have the largest volume. So like I want to be able to get the biggest box I possibly can out of this piece of cardboard so it'll hold the most stuff. So I don't know how big of a square to cut out of the corner. Therefore, I should call the dimensions of the square what?
Unknowns.
And what's the most common thing to call an unknown?
X.
X, there we go. So these are X. Okay, perfect. All right, so can you picture how this is gonna look? Like you're gonna cut this little corner out here, and you're gonna cut this corner out. You're gonna cut this corner.
So are we gonna have to find the area of the smaller squares?
We are just gonna use their dimensions. So you won't have to find their area, no. But we are gonna use you have to put that dimension into our volume formula. Okay, let's talk about that. So this X, like I cut it out, right? And I fold up the sides and I fold up the other sides. What does this X become in relation to the box?
The height.
Right, this becomes the height. So like, if I were to draw the box, okay? When we fold this thing up, these X's, like, I don't have a piece of paper ready here, but like the X's come together and become the seam along the corner of the box. It becomes this part right here. All right, if you were to, I made a dotted line right here and a dotted line right here and here and here. And if you fold on the dotted lines, these two pieces are gonna come together, right? And they're gonna make a seam, and that's gonna be the height of the box. So I'm actually gonna put that right there in our volume formula. Now, you can see we cut some stuff out of this piece of cardboard here. So like our length and our width are not going to be 3 anymore because we cut some stuff, some of it out. So what would be this right here? How long would,
3 minus 2x.
yeah, very good. 3 minus 2x. Okay. So once again, picture folding this on a dotted line. That would be like right here, 3 minus 2x. So we could call it you can call it the length if you want to, or you can call it the width. It doesn't matter. I'll put it in for length. So what will be this dimension right here? Because this also is not going to be 3 because we cut some of it out. So what will this be?
Same thing.
Same thing, right? Because you're taking this x and this x away from the total. The total here is 3, so minus x, 3 minus 2x. Okay. All right, so that ends up being your width. And now we have a volume formula, all in terms of one variable. So the only thing left to do is to take the derivative of this and set it equal to 0 and make sure we get a reasonable answer, okay? So I don't know, I think we should just multiply it out. This is 9, let's see, 6 minus 12x plus 4x squared times x. So 9x minus 12x squared plus 4x cubed. Check me on that. Yeah, I think that's good. All right, and then take the derivative of it. What's the derivative when you do that?
9 minus 24x plus 12x squared.
Good. And then that's a quadratic. So, oh, we could take so we're setting this equal to 0. I'm going to rewrite it so that it's in descending order. Okay. So we could take a 3 out of all of that, right? Take a 3 out. So this would be 4x squared minus 8x plus 3. And then that's a trinomial. So what multiplies to 12 and adds up to -8?
-6 and -2.
-6, -2. Okay, good. So (4x squared minus 6x minus 2x plus 3 equals 0. Take a 2x out, 2x minus 3. Take a -1 out. And you can write this in any order and it'll still work out. Same thing. So 2x minus 1, 2x minus 3. So one of your answers is 1/2. Your other answer is 3/2. Okay. All right. So if I use x equals 1/2, then that means like all these little squares have dimensions of 1/2. Like that. I'm just writing the ones on the bottom just to so I don't have to write them all. So if this is 1/2 and this is 1/2, oh, this would be 3 minus 2 times 1/2. What is 3 minus 2 times 1/2?
2.
2. So this length right here would be 2. This would be a half. This would be a half. That's going to work out just fine because 2 plus a half is going to add up to 3. Okay, so that means that that's fine. You could make a box like that. Okay, now if I use the 3/2, and this is where checking if your answer is reasonable is so important. If I use 3/2, then this would be 3/2, and this would be 3/2, and this would be 3 minus 2 times 3/2. What is 3 minus 2 times 3/2?
That's 0.
0.
0, yeah. So that's not gonna work, right? Because we can't have a length of 0. We don't have a box anymore. You got more like an envelope, okay? So we have to throw the 3/2 out and only use the x equals 1/2, okay? So your dimensions would be x equals 1/2, what are we going with here, feet? So that would be like your, what do we call that? Your height of your box, and your length and your width would be 3 minus 2x, which you already found for me, which was 2 feet each. So you would have a 2 by 2 by 1/2 foot box. And that would be the optimum volume that you could create out of a piece of cardboard that was 3 feet by 3 feet. Okay. This is huge for engineering, definitely. Actually, for business also. Okay, so that's where I'm going to stop for today's notes, and it's like 10:07, so it's a decent time too. The Zoom work for today is a problem, just one problem, very similar to what we just did. So like you're in the zone, you're in that thought process already. And so Zoom, if you go on Canvas, it's posted there. It's a PDF, and it's a diagram and one problem that you need to work on in your groups. All right. So I'm going to stop the recording